Out. Any question from previous part? Okay. Any question from previous part? No questions? Okay. Okay, we continue with one example. A SUF system consists of a mass of 20 kg and a spring of stiffness 4000 Newton per meter. The amplitude of successive cycles are found to be 50, 45, 40, 35, and so on. Determine the nature of and the magnitude of damping force and the frequency of the damped vibration. Okay, so here, according to the amplitudes for the consecutive cycles, we need to obtain the nature of the damping in our system. Here, the amplitude is decreased linearly, as you can see, by 5 millimeter. In each cycle, the amplitude is decreased by 5 millimeters. So, as you can see from the first cycle to the second one, the amplitude is decreased by 5. From second one to third one is decreased by 5. So, it's decreasing linearly. According to this condition, we can conclude that the damping of this system is a column damping. Okay, so because the amplitude of the successive cycles diminish by 5 millimeter, system has column damping. It's decreasing linearly. So you know that when the damping in the system is column, or we have a system with column damping, the natural frequency will be remain the same. And but in the system with viscous damping, the natural frequency of the system decreased. As you know, we have the frequency of the damped system, omega d. But here we have a system with column damping, so the natural frequency is the same as an undamped system, and it's equal to square root of k divided by m. Here we have the stiffness and the mass of the system, so easily we can calculate the natural frequency, and also the force or the magnitude of the damping force in the system, which is equal to mu times by n, can be calculated from the amplitude decrement. Here in each cycle, the amplitude is decreased by 5 millimeter. Here you can see, if you compare these results, in each cycle the amplitude is decreased by 5 millimeters. So we know that the decrement in each complete cycle for a system with column damping is equal to 4 times by mu n divided by k. So, and it's equal to 5 millimeter or 0.005 meter. And then we can find the mu n from this equation, because k is given data, it's equal to 4000 Newton per meter. And we can calculate that mu n is equal to 4,000 times by 5 millimeter divided by 4, and it's equal to 5 Newton. So this is the damping force in each cycle. Any question? Is it clear?
Say the value of n is 5.
The value of mu times by n, because from this equation, here in this equation, we know that the amplitude is decreased in each complete cycle is decreased by 4 times by mu times by n divided by k, and this is the decrement in each cycle. And from the given data, we can see that the amplitude is decreased by 5 millimeter in each cycle, from 50 to 45, from 45 to 40. So the amplitude is decreased by 5. So this term must be equal to 5 millimeter, or we should convert it into meter. And from here, we can extract the mu times by n, because according to the problem description, we need to calculate the magnitude of damping force. The magnitude of damping force here, because this is a system with column damping, and the magnitude of the column damping force is equal to mu times by n. So from here, we can solve this equation for mu times by n, and we can conclude that mu times by n is equal to 5 Newton. This is
Okay.
this n is for Newton. It's not the same n. Okay.
Okay. Thank you, sir.
Okay. Any other question? Clear?
Yes, sir. Clear.
Okay. Okay. We want to find the equivalent viscous damping constant for a column damping force sinusoidal vibration. Here, in fact, we have a system with column damping, but we want to find an equivalent viscous damp system for a system with column damping, with friction. So to find the equivalent viscous damping constant, we need to find the energy dissipated for each cycle. And from the previous part, previous chapter, we know that if we assume that the displacement is a harmonic function, such as xt is equal to uppercase x times by sine omega t, which omega is the frequency of the excitation. So we can conclude that the energy dissipated in each cycle from previous chapter, we know that it's equal to 4 times by mu times by nx. So from this term, and also we know in a viscous damp system, for a viscous damp system, the energy dissipated in each cycle is pi c times by omega times by x squared, again with the same displacement function. So if we use these two equations, we can extract the equivalent C for a system with column damping, and it's equal to this term divided by coefficient of C in this equation, which is pi times by omega times by x squared. And if you simplify this term, you can extract this expression for the equivalent coefficient for the damping uh, constant. It's equal to 4 mu n divided by pi omega x. So if in a system with column damping with a friction mu, if you want to find an equivalent system with viscous damping, you can use a damper with this coefficient. So instead of the friction, if we had a damping, viscous damping in the system with this constant 4 mu n divided by pi omega x, the response for them will be the same. Of course, this is only an approximation, and this results is validated only when we have the harmonic excitation. I mean here, by this assumption that the system is under the harmonic excitation, we know that the response is something like this, the x, and according to this assumption we extract this equivalent uh, viscous damping constant. So for this case we can use this equivalent damper, and if you want to extract the response for the system subjected to a harmonic excitation, you can use this equivalent and you can solve the equation of motion. I mean, instead of that nonlinear equation, you can use this equation, which is a linear, which is m times by x double dot plus c equivalent, which this c equivalent in fact is this term times by x dot, and finally plus k x is equal to ft, which I told you that ft is a harmonic excitation f sine omega t. So according to this condition, we can solve this equation and extract the response for a column damped system. You know, if the system was a column damped, the equation of motion is nonlinear, and we need to solve the equation for each half cycle. But here, according to this equation and this equivalent viscous damping constant, we can solve a linear equation and obtain the response of x in uh, terms of time. Clear? Any question?
No, sir.
Okay, the next example, there is a mass of a spring mass system. Here we have this mass which is connected to two springs with stiffness K on a dry surface inclined as shown here. We have the friction on this surface. Derive the equation of motion, part A, and part B, find the response of the system for the following data. When M is equal to 20 kilogram, K is equal to 1000 Newton per meter. The coefficient of friction mu is 0.1, and the initial condition x naught is 0.1 meter and v naught is 5 meter per second. So here we have a system with column damping because we have friction. We need to extract the equation of motion. Using the Newton's second law, you can easily find the equation of motion for this system, which similar to a simple mass and a spring system. The equation of motion is a function of, or it depends on the direction of motion, the direction of the velocity x dot. So we can extract the equation of motion for two different cases. The case one, when this mass m is going down, for this case x dot is positive. As you can see, for this case, when x dot is positive, x can be positive or negative. The equation of motion for this case is equal to mx double dot plus 2kx plus mu mg cosine theta is equal to 0. So if you plot the free body diagram, when this mass m is going down, we will have one force due to this spring, k times by x, and also another force here due to the second spring. Both of them have the same stiffness, K. So the force in both of them are equal to K times by X. Also, we have one normal reaction, which is not appear into the equation of motion when you are writing the equation of motion in X direction. This force N is perpendicular to the direction X. So it will not appear in the equation of motion in X direction. And also we have the friction. When this mass M is going down, the friction is in upward direction, and it's equal to mu times by N. And also we have the weight. which is mg. Here, first we need to calculate n. If you write the force equation in y direction, which y is perpendicular to x-axis, if you write the force equation in y direction, we will have the summation of the force in y direction is equal to what? Can you tell me? We are writing
Weight,
the, sorry, what is the,
weight force,
what?
weight force and the normal force.
Yes, no. In the right hand side of the equation, I'm writing the Newton's second law. In the Newton's second law, we will have the summation of the force is equal to the mass times by the acceleration. My question is, what is the right hand side of this equation? We are writing the force equation in y direction. We know that the summation of the force in y direction is
Is equal
equal
to
to,
0.
is 0. Yes, because there is no motion in y direction. So it will be mass times by the acceleration, because there is no motion, so acceleration is 0. And the summation of the force in y direction, we will have one normal reaction n, and also we have mg, which mg will have two components in x direction and y direction. The y components for the weight is mg times by cosine theta, so it will be minus mg times by cosine theta, and right hand side of the equation, which is 0. So from here, from this equation, we can conclude that n is equal to mg times by cosine theta, and this is the normal reaction, this term into the equation. And now we can write the force equation in x direction, but pay attention, when you are writing the force equation for a vibrating system and we have weight and initial deflection, again you should use that point that you can neglect the weight in your equation, and also you should ignore the initial deflection in these two springs. So when you write the force equation in x direction, it's equal to, in the right hand side of the equation, we will have m times by x double dot. This time x double dot is not 0 in when you are writing the force. In the y direction, the y double dot was 0 because there is no motion in y direction, but in x direction we have motion, so we will have x double dot. And the force equation in x, if you write the forces, we will have minus kx for this spring. We have another kx, so it's again minus kx, which x is measured from the equilibrium position, and we neglect the initial deflection of the springs. As I told you, because we are neglecting the initial deflection in the springs, we neglect this mg sine theta as well. So there is no weight in the equation of motion in x direction. And also we have this mu n, and it's in negative direction, so it will be minus mu times by n, and there is no other forces in x direction. It must be equal to mass times by the acceleration. So if you simplify this equation, you can extract the first equation for case 1 when mass m is going down. It will be mx double dot when you move minus kx minus mu n to the other side of the equation. We will have mx double dot plus this term will be minus 2 times by kx. When it moves to the right hand side of the equation, it will be plus 2kx, as you can see here. And finally plus mu n, which n is equal to mg cosine theta. So this is the first equation. For the second case, when the mass m is going up, the x dot is negative, or the direction of the speed, the velocity is in opposite direction of x. In this case, when mass m is going up, the friction force is in downward direction. It will be mu n. Again, n will be obtained from the previous equation, and it's equal to mg cosine theta, similar to the equation 1. Only the direction of mu will be changed. And if you write the force equation in x direction, it's equal to mx double dot. The force equation in x direction, this time mass m is going in upward direction, so the force for k is in downward direction. They are positive, so we will have kx plus mu n is equal to minus mx double dot. Okay, so you can plus kx plus mu n is equal to mx double dot, of course minus mx double dot, because the direction of the motion is this time is in upward direction, and we will have sorry, the direction of mu n, I think it's let me check it, because here we have kx when it's going up, and is in downward direction. For the first case, when m is going down, the mu n is in upward direction, so all of them are negative. But in the second case, mu n is in downward direction, so we will have here we will have minus kx. This term is as well minus kx plus mu n minus mx double dot. Or this term, when we consider for kx, we consider negative, here it will be positive. And when you simplify this equation, you can extract the second equation. The difference between this case and the first case is only the direction of mu n. And according to this direction, the equation of motion will be mx double dot plus 2kx minus mu mg cosine theta. So if we ignore the non-homogeneous term for this system, the equation of motion, the homogeneous part, is the same. As you can see, for both direction of motion, the equation of motion is mx double dot plus 2kx. But by changing the direction of motion and changing the direction of the friction force, we will have the non-homogeneous term. Now we need to solve this equation for two different cases with two different initial conditions. The first initial condition is used for x naught, and let me check the initial condition. Here is x naught is 0.1. It means that the initial condition for the first case is when m is going down, and it's located, for example, someplace here, and this distance is 0.1, and the velocity, the initial velocity, is 5 meters per second. So it's in positive direction of x. In this case, we can solve the equation of motion. And for case 1, if you solve the equation of motion, this is the response according to the sign of non-homogeneous term. Here for the case 1, you can see this is the sign of non-homogeneous term. According to the sign here, you can obtain the sign of the non-homogeneous term. So the solution for the particular response is a constant value, as you can see, because mu mg cosine theta is a constant value. The mass g cosine theta and mu, all of them are constant. So the particular response is a constant. When you substitute into the equation of motion, the derivative of xp is 0, so we will have 2k times by the constant value c plus mu times by n, or mg cosine theta, it's equal to 0. So from here we can conclude that c is equal to minus mu n divided by 2k, and this is the non-homogeneous solution for case 1, as you can see, and it's equal to mu n, or mg cosine theta, divided by 2k. And for the second case, this time we have a negative, and if you substitute the xp is equal to a constant value c, you can solve this equation and you can obtain the particular solution as plus mu mg cosine theta divided by 2k. The homogeneous solution is the same for both of them, is a1 cosine omega nt plus a2 sine omega nt. And for the second case, only the constant coefficients are different, because as you can see, the initial conditions are different, so the constant coefficients will be obtained different. So we need to solve these two equations for the first initial condition. Using the first initial condition, because the displacement is positive and the velocity is positive as well, so we need to use the case 1. For the case 1, we have this solution x1t, a1 and a2, so we need to obtain a1 and a2 from the initial condition. When t is equal to 0, x is equal to 0.1, so here we need to substitute, instead of t, we need to substitute 0. We will have a1 times by cosine 0 plus a2 times by sine 0, which is 0 this term, minus the particular response is equal to 0.1. And by solving this equation, we can obtain that a1 is equal to this term. And the second boundary condition is the velocity at t is equal to 0 is 5. So we need to obtain the x dot, the derivative of x1 with respect to time. When you calculate the derivative of x1, it's equal to minus a1 times by omega n times by sine omega nt. And when you substitute t is equal to 0, it will be sine 0. This is the first term. The second term, a2 times by omega n times by cosine omega nt, which when you substitute t is equal to 0, it will be a2 times by omega n times by cosine 0. And the derivative of this term, which is a constant value, is 0. So we will have this term, it must be equal to 5. And when you solve this equation, you can extract that a2 is equal to 5 divided by omega n. Now we can substitute a1 and a2 into the first solution, and the response is this term. The next step, we need to use x1t to obtain the initial condition for x2. Any questions so far? Is it clear?
Yes, sir.
Okay. Now we have x1 and we need to obtain the initial condition for the second half cycle. For this purpose, we should know that when this mass will be stopped, I mean, here, let's back to the figure. Here, this mass m will start from some point, for example, here, start here with initial velocity 5 meters per second. It will go down and will stop in some places, for example, here, and again start the motion to the upward direction. We need to obtain this point. If we call it, for example, t0, we need to obtain t0, that in this point the velocity of this mass is 0. For this purpose, we need to find the velocity of x1t and find at which time this velocity is equal to 0. Here we have x1, so this is x1t. Now we need to find at t is equal to t naught, which the velocity is equal to 0. We need to calculate this t naught. So we need to obtain the derivative of x1 with respect to time. The derivative of x1 with respect to time is equal to this term. Here we have one cosine function, one sine function, and one constant term. The derivative of cosine omega nt is minus omega n times by sine omega n t. This is the first term. The second term is the derivative of sine omega nt, which is omega n times by cosine omega nt, which omega n will be cancelled out with this omega, and we will have the second term, and the derivative of this term is 0. So at t is equal to t naught, the velocity must be equal to 0, or at t is equal to t naught, this term must be equal to 0. From this equation, you can solve and obtain the tangent of omega n t naught for this equation, which is equal to this term. And then you can substitute into this equation, you can substitute the numerical value m, theta, and k, and also mu. We have all of this information, and also we know how much is omega n, which is equal to a square root of k divided by m. Of course, we have 2k here. So this is the tangent, and we can calculate the t naught or t sub 0, which is 0.1357 seconds. After this time, the mass m will start to go up. So at this time, we can calculate the velocity and also the displacement of x1, which are the initial condition for the second half cycle. So x2, if we assume another new origin for the time, for x2 at t is equal to, of course this is t prime, in fact t prime is equal to 0 because this is a new origin for time. x20 is equal to x1 at t naught, and also the velocity for x2 at 0 is the velocity for x1 at t naught. So we can substitute and obtain the initial condition. Here you need to in x1t, if you substitute t is equal to 0.1357, you can obtain x20, sorry, the initial condition, and x2.0 is 0 because we know at this moment when t is equal to this value, x1 dot is 0. We use this condition to obtain t naught. So we know that the velocity for the initial condition in the second case is 0. So we can use these two equations to obtain the initial the constant coefficient a3 and a4. So in the second equation, here in previous slide, x2, we have the solution. This is the x2. This is the x2, and now you can use the initial condition to obtain a3 and a4. So here you can see when t is equal to 0, a3 times by cosine 0 plus a4 times by sine 0. As you can see, we substitute t is equal to 0 because this t is different from this t, okay? Or we can call it, for example, t prime, maybe it's better. So at t prime is equal to 0, t is equal to 0.13 second. So we can solve this equation, a3 times by cosine 0, this term is 0, and here we will have a constant value. It must be equal to this term, 0.503. When you substitute t is equal to 0.1357 in this equation, you can obtain that x1 is equal to this value, 0.503. And from this equation, you can obtain A3. And from the velocity, you can find the derivative of x2 with respect to time, which is minus A3 omega n sine omega nt plus A4 omega n cosine omega nt. And when you substitute t is equal to 0, this term is 0, and you only have, because cosine of 0 is 1, so it will be A4 times by omega n. It must be equal to the velocity for x1 dot at t is equal to 0.1357, which is 0, and we can conclude that A4 is 0. So this is the response for the second half cycle, and this procedure will be continued. I mean, if you want to find the response in the third half cycle, you need to use again x1 as your response, but this time A1 and A2 will be obtained from the initial conditions, from the new initial conditions, and these new initial conditions are obtained from x2. And again, you should find the derivative of x2 with respect to time, and find the time that in this time the velocity is 0, so you can obtain the t1 similar to t naught, and then solve the third half cycle. So this procedure will be continued till the mass m will be stopped. Okay, any question? Is it clear? Okay, if you don't have any question, we can wrap up this session and continue tomorrow.
Thank you, sir.
Okay,
Thank you,
any
sir.
other question?
No, sir.
No, sir.
Okay, thank you and have a good day. So we continue tomorrow. Thank you.